Section 3.4, linear programming. Linear programming is a technique that identifies the minimum and maximum value of some quantity. This quantity is modeled with an objective function. The objective function is going to have variables such as x and y variables. With those variables, we have limits on them. And those limits inside the objective function are going to be constraints. Those constraints on those variables are going to be written as linear inequalities. So we're going to combine our objective function and our inequalities onto a graph and determine the values that are maximum or minimum values that we need to solve our objective. Objective function is a model of the quantity that you want to make as large or as small as possible. Now, the constraints are going to be the restrictions on the variables of the objective function in a linear programming problem. What happens is we graph the inequalities of our constraints, and then we generate a feasible region. In other words, all values that will solve our objective function. But what we want to do is find the values that satisfy the constraints and also the objective function. But the objective function, we're either looking for a maximum or minimum, depending on the problem that we're trying to solve. Inside that region, we're going to have vertices. A vertice is the intersection of two lines. So they has to form an angle. The vertex principle in linear programming is if there is a maximum or minimum value of a linear objective function, it occurs at one or more of the vertices in the feasibility region. Let's take a look at our first linear programming problem. Here they want us to find the values of x and y that maximize and minimize c. Here, c equals x plus y is our objective function. We have constraints on x and y, and of course our constraints are going to be inequalities that we need to graph. So we need to graph each of these three inequalities, find our feasibility region, and then find the vertices that are going to be part of our solution for C. And we want to find the vertices that maximize and minimize C in this problem. So let's start out with graphing x plus y is less than or equal to 5. So there, what we're going to do is just solve the problem for y. Y is less than or equal to, subtract x on both sides, I get a negative x plus 5. My slope is a negative 1. My intercept is 0, 5. Graphing that first inequality, I'm going to get 0, 1, 2, 3, 4, 5. My slope is a negative 1, so I go down and to the right 1, down and to the right 1. That is a less than or equal to, so that will be a solid line. What I need to do is to shade the solution for my inequality, but I'll wait after I graph these next two values. Next, I'm going to have y is greater than or equal to x. So that's already solved for y. So here my slope is a positive 1, and my intercept is 0, 0. Graphing, 0, 0, up 1 over 1, positive slope, up 1 over 1, positive slope. The inequality is greater than or equal to, so again, this is a solid line. I still need the shade, but I'll wait. And then my last constraint is x is greater than or equal to 0. And I need to graph that. To do that, I'm going to create a table, x, y. X is 0. And I can pick any value for y. And then I can graph 0, 0, 0, 1, and 0, 2. That line is going to be solid because of the greater than or equal to. I have my inequalities graphed. Let's identify our vertices. Our vertices are going to be the intersection points of the lines. Notice they intersect at a point and they create an angle. And in this situation, I have 3 intersection points. What I need to do is actually find my feasibility region, and that is going to be done by determining the shading of my inequalities. Here, y is less than x plus 5, so that's my blue line. So that would be below the blue line. The green line, y is greater, so it would be above the green line. And for my red line, I have x is greater, and that would be to the right of the red line. When I figure that all out, the shading will all intersect inside of this triangle. Therefore, all values inside this triangle will be a solution to my objective function, which is given here. But what I want to determine are the values that make this a maximum or minimum value to solve the problem. The maximum or minimum values are going to be determined by the vertices. And what I have are 3 intersection points. My 3 intersection points that are possible solutions are going to be 0, 0, 0, 1, 2, 3, 4, 5. The third point is determined by this intersection point. But if we go back to the blue line and green line, we see that the slope of the blue line is a negative 1. The slope of the green line is a positive 1. Therefore, we know that they are negative reciprocals and that these 2 lines must be perpendicular. If that's the case, we know they intersect at the midpoint of each of the x and y vertices. Therefore, I know that that intersection is 2.5 and 2.5. So 2.5 and 2.5 is going to give me 5 halves and 5 halves. To determine the maximum and minimum value of each point, all I do is substitute into the objective function. Some may be maximums, some may be minimums, some may be neither. But we have to substitute in to determine that. Here, when I substitute 0, 0, I get c equal to 0. When I substitute in 0 and 5, I get c equal to 5. When I substitute in 5 halves, or 2.5 and 2.5, I end up with c equal to 5. So 0 must be the minimum value. 5 and 5 are both maximum values. So in this instance, each vertice is either a minimum or a maximum. Here, 0, 0 for x and y is a minimum. 0, 5 is a maximum. And 5 halves is a maximum. Other problems will give us constraints that only give us a minimum or a maximum, and another point might be neither. Let's take a look at another linear programming problem. Again, they want us to find the values of x and y that maximize and minimize p. Our constraints: x is between 6 and 1, y is between 2 and 4, x plus y is greater than or equal to 4, and our objective function p equals 3x plus 2y. With the first 2 constraints, we can graph them by knowing that anything that has just an x value is going to be a vertical line. Here, I'm going to have a solid vertical line at 1 and a solid vertical line at 6. So I can graph those. Two, 3, 4, 5, 6. I also know that the shaded region for this constraint is going to be in between the 2 red lines because x is less than 6 but greater than 1. I can also graph my y value constraint knowing that it is greater than 2 and less than 4. And those will be horizontal lines at 2 and 4, and again, those will be solid lines because of the inequalities that's given to me. 3 and 4. I know that the shaded region will be in between these two green lines because of the inequality given. So already I'm given 4 vertices. These may or may not be my vertices inside my feasibility region. What I need to do to determine my feasibility region is to graph my linear inequality, and that will help me determine what that region will be. So here I'm going to solve that inequality for y. So y is greater than or equal to a negative x plus 4. Here I have a slope of a negative 1, a y-intercept of 0, 4. So I can graph the y-intercept at 0, 4, 1, 2, 3, 4. And I can use the slope, which is a negative 1, which will be down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. My line is going to be a solid line because of the inequality. Now what I need to do is determine my feasibility region by looking at the inequality symbols. I know that the red lines for my x between 1 and 6 is going to be inside the red lines. My y value between 2 and 4 is going to be inside my green lines. And for my linear inequality, the y values are greater than this relationship. So that's above the blue line. So my feasibility region will be anywhere above the blue line and in between the greens and red lines. Now I just determine the vertices generated by those intersections, and those will be the possible maximum and minimum values for my solution given this objective function. So let's label those intersection points. I have 1, 2, 3, 4, 5 of them. First, I have 1, 1, 2, 3. I have 1, 4. I have 2, 2. I have 1, 2, 3, 4, 5, 6, 2. And 6, 4. I substitute each ordered pair into the objective function and determine which ones are minimums, maximums, or neither. So when I substitute 1, 3 into this function, I'm going to get 3 times 1 is 3, plus 6 is going to give me 9. So P is 9 for that ordered pair. 1, 4 is going to give me 3 plus 8, which is 11. 2, 2 is going to give me 6 plus 4, which is 10. 6, 2 is going to give me 18 plus 4, which is going to give me 22. And my last ordered pair is going to be 6, 4, which is going to give me 18 and 8, which will be 26. Therefore, if I take a look at each vertice, I can determine that this ordered pair is my minimum, and the last ordered pair is my maximum. In our last example for linear programming, we're going to have to generate the constraints and also our objective function. So let's read. A furniture company can make from 30 to 60 tables a day and from 40 to 100 chairs a day. It can make at most 120 units in one day. The profit on a table is $150 and the profit on a chair is $65. How many tables and chairs should they make per day to maximize their profit? How much is the maximum profit? Well, let's start labeling. I'm going to let T equal our tables and our C equal the chairs. And just like in our X, Y axis, I'm going to put them alphabetical. So therefore, our C will represent our x-axis, and our T will represent our y-axis. So I can label that right now, that here I have my C, and here I have my T. Let's take a look at some of the constraints inside the problem. They give me my first constraint stating that they can generate anywhere from 30 to 60 tables a day. Therefore, I have a constraint where T is less than or equal to 60 and greater than or equal to 30. The next one is that they can generate anywhere between 40 to 100 chairs a day. That means that C is less than 100 and greater than or equal to 40. I also know that at most they can make 120 units combined. Therefore, T tables plus C chairs is at most 120 units. Therefore, that is less than or equal to 120. Now, they want us to determine the maximum profit. Therefore, that is our objective function. P is equal to the profit per table, which is 150 T, added to the profit per chair, which is 65 C. So we must graph our constraints, find our feasibility region, determine our vertices, substitute into our objective function for our profit, find the maximum, and then determine what is that profit. Let's start with the constraints. I have T is less than or equal to 60, but greater than or equal to 30. I'm going to let each one of these lines represent 10 units. Therefore, T is between 60 and 30, 10, 20, 30, and that is a horizontal line. Recall that we let T be a value for Y, and 60, 40, 50, 60. Another horizontal line. And I know the shaded region would be between those lines because T is between 30 and 60. C is our value for X. Those will be vertical lines. And I know that will fall between 40 and 100. 10, 20, 30, 40. 50, 60, 70, 80, 90, 100. And I know the shading for that will fall between 40 and 100 because that's where C lies, between 40 and 100. Now, I need to graph our linear inequality, T plus C is less than 120. When I do that, I'm going to let C be X, T be Y. So therefore, I need to solve for Y. And in this instance, it's going to be T. So I'm going to solve for T. So T is less than or equal to a negative C plus 120. What I want to do is generate a table. So I make sure that I fall in between my region that I know is shaded by my red and blue lines. That will be values of X that are 10, 20, 30, 40, 40 to 100, which are given by my other constraint. So if I start at 40, I let x be 40, which in this case is c, and y would equal t. 40, which is a negative 40, gives me 120, which gives me 80. 50 is going to give me 70. 60 is going to give me 60. 70 will be 50. And I think we can get the picture so we can start graphing. So I'm going to have 40, 10, 20, 30, 40, 10, 20, 30, 40, 50, 60, 70, 80, 50, 70, 60, 60, 70, 50, 80, 40, 90, 30, and that should take us through our feasibility region. So I'm going to generate that line. Now I just need to generate my shading for each one of my inequalities. I know that I'm going to fall in between my blue lines and my red lines. And for the green line, I have t is less than or equal to, so it's going to be below the green line. So my region will be in this shaded area. Now that I have my feasibility region, I can use the vertices to find the max for my objective function. My ordered pairs for those vertices are going to be 10, 20, 30, 40, 10, 20, 30, 40, 30, 40, 60, 60, 60, and 90, 30. Recall, I substitute these values into my objective function and determine the max and min. We've determined the ordered pairs for the vertices to be 40, 30, 40, 60, 60, 60, 90, 30. Now we take those ordered pairs, substitute into the objective function, and determine the maximum. For the first ordered pair, I got $7,100 profit. For the second one, $11,600 profit. For the third one, $12,900 profit. And for the fourth one, $10,350 profit. Our maximum ordered pair would be 60 tables, 60 chairs, and our profit in that situation, answering the second question, would be $12,900.